Well, hello ladies and gentlemen. Today I'm talking to you on a fine Scottish November morning. Not even being sarcastic, it's actually nice out, which is a surprise. Today I'm going to talk to you about costs of resistance. Costs of resistance to parasitism. So one of the big questions in evolutionary ecology is why susceptible individuals exist. Surely parasites should have eliminated variation in susceptibility and selected for resistant host populations. Hasn't happened. There are susceptible individuals, and there are a good few hypotheses to explain why this is going on. I'm going to talk about one of them today. So one hypothesis is that hosts that are resistant to parasitism pay a cost for that resistance, that they're crapping another important fitness trait. For example, fecundity. So here's a common test. You'd have hosts that are super resistant, they have low fecundity, whereas your susceptible hosts have high fecundity. It's all part of the experience here. It's all rock and roll, high caliber materials for support. Yeah, so costs of resistance. Now, people have been studying this for ages, and there have been some incredibly cool studies done, especially in the lab. But we know very little of how costs of resistance vary across wild populations. Populations that have been subject to natural selection as opposed to, artificial selection in the lab. Now, one of the reasons why there hasn't been so much work on this, it's really hard to do. You need a natural host parasite system that varies in the wild, that you can work with everything, that's amenable in the lab. Well, we've had a go at this. We have one of those systems. We've been looking at Daphnia dentifera, which is a freshwater planktonic crustacean, and its natural yeast parasite, Mechnicaria bicuspidata. It's a mouthful. Mech for short. So we went out and collected Daphnia, wild Daphnia, from before and after parasite epidemic, Mech epidemic, in 5 natural lake populations in the US state of Indiana. Now, one cool thing about Daphnia is that they can reproduce both sexually and asexually. So what we did is we took these Daphnia from the wild and we propagated them asexually in the lab. So we have a genetic snapshot of wild populations before and after the epidemic. We could also do replicated experiments with the same individual. So we've got these isofemale lines that we can expose to the parasite and take a measure of resistance, and then in separate beakers we can keep them on their own and measure fecundity. That's what we did, and we could make estimates of how resistance and fecundity are related to each other. What did we find? First of all, we found that host lines collected after the parasite epidemic were much more resistant than those collected before the epidemic. This might seem unremarkable, but this showed that parasite-mediated selection was going on. Parasites were having an effect on the host population and selecting for resistance. This parasite's important. We also found a cost of resistance, yay, but we found it in 2 of the 5 populations. We found variation in cost of resistance. This is the cool bit right here. So, to go into more details of why we got variation, we have to think about what is driving, what's the mechanism behind this cost. Well, Spencer Hall and his lab have done some interesting research on this. And he's shown that big Daphnia eat more, and they have more babies. It's unremarkable. But big Daphnia are also more likely to consume parasite transmission stages, because they filter more, right? So this cost of resistance is dead simple. It's just you're big, you have more babies, but you're more likely to be exposed to the parasite. And that's what we think is going on in 2 of the 5 populations. Now, what about the 3 that aren't showing a cost of resistance? Well, you have to remember that exposure to the parasite is only half the story. Hosts will vary intrinsically in their resistance. So for a given exposure, some hosts may have better immune responses, some hosts might have the right receptors in the gut for the parasite to get in. This is varying too. So when we measure resistance, we've got a bucket trait for the likelihood of the host encountering the parasite and then resisting once that's happened. Interestingly, the hosts that did show a cost of resistance, so did have a trade-off between resistance and fecundity, those populations had a comparatively small parasite epidemic in the previous year. So you can imagine that variation in exposure would be really important. 2 of the 3 populations that didn't have a cost of resistance, no significant relationship between fecundity and resistance. In those populations, there were big epidemics in the previous year. So here you might expect that if there are a loads of parasites in the lake, then variation in exposure rate might become a lot less important, because even your tiny Daphnia is still highly likely to encounter the parasite, and their selection will be on intrinsic resistance. That's what we reckon is going on. Of course, a lot more work needs to be done to fully dissect this out, because what we've got is just overall resistance. Nevertheless, this is really important in that it shows that costs of resistance vary in wild populations. Because people have studied costs, and sometimes they find it, sometimes they don't. But what we have is a system that showed that it varies over space. The next step, does it vary over time? That's going to be really cool. So thank you for listening. I hope this is of some interest. And please contact me if you have any questions or want to know more. So the paper is all that out, 2013. It's in the Journal of Evolutionary Biology. Be on my website. And it was done at the Georgia Institute of Technology, funding from the NSF. Yeah, that's it for today.